In the depths of space, billions of light years from Earth, something is terribly wrong. Astronomers have discovered massive regions of the universe that have gone dark. Cosmic dead zones where hundreds, sometimes thousands of galaxies have stopped forming stars. These are the galactic graveyards, and they span distances so vast that light takes millions of years to cross them. What we're looking at is not a natural end, but mass extinction on a scale that defies human comprehension. Entire galaxy clusters, structures containing more matter than 1 trillion suns, have fallen silent. The stellar nurseries have closed. The cosmic forges have cooled. These galaxies are dead, and we're only now beginning to understand what killed them and why their corpses cluster together in specific regions of space like victims of some cosmic catastrophe. A galaxy is alive when it forms stars. This is the fundamental truth of galactic existence. Star formation is the heartbeat of a galaxy, the process that defines whether it's thriving or dying. Inside the spiral arms and dense clouds of every living galaxy, hydrogen gas collapses under its own gravity. The pressure builds. The temperature rises. Eventually, nuclear fusion ignites and a star is born. This process repeats billions of times, creating the spectacular light shows we see when we point our telescopes at distant spirals like Andromeda or Triangulum. Young, massive stars burn blue and bright, pumping out intense ultraviolet radiation that makes the galaxy glow with the vigor of youth. But star formation requires fuel, specifically cold molecular hydrogen gas. A galaxy needs enormous reserves of this gas to continue producing new generations of stars. When that gas runs out or gets stripped away by external forces, star formation stops. The existing massive blue stars burn through their fuel in mere millions of years, exploding as supernovas and leaving behind only their smaller, longer-lived siblings. These remaining stars, the red and yellow dwarfs, emit a cooler, redder light. Over time, the galaxy's color shifts from vibrant blue to a dull, lifeless red. This color change is the visual signature of death. A red galaxy is a dead galaxy, filled with ancient stars slowly fading away with no replacements being born. The transformation takes billions of years, but the outcome is inevitable once the gas is gone. 300 million light-years from Earth sits the Coma Cluster, one of the largest structures ever discovered. This massive congregation of galaxies contains over 1,000 individual systems bound together by gravity, orbiting a common center of mass. When astronomers first studied the Coma Cluster in detail during the mid-20th century, they noticed something deeply unsettling. Most of these galaxies were red, not just a little red, but completely dominated by old, cool stars with no signs of active star formation whatsoever. Galaxy after galaxy showed the same lifeless spectrum. The same absence of young blue stars, the same cosmic exhaustion. This was humanity's first clear view of a galactic graveyard. The Coma Cluster became the archetypal dead zone, the place where we learned that galaxies don't just live forever in isolated splendor. They can be killed, and when conditions are right, they're killed in massive numbers all at once. Further observations revealed that the dead galaxies weren't randomly scattered throughout the cluster. They concentrated toward the center, in the densest regions where the space between galaxies fills with superheated gas at temperatures reaching tens of millions of degrees. The few living galaxies that remained, still blue and forming stars, huddled at the cluster's outskirts, as if trying to escape the killing zone at the core. The Coma Cluster taught us that galaxy death is not a solitary affair. It's a mass phenomenon, a coordinated extinction that occurs when hundreds of galaxies fall into the same hostile environment simultaneously. Watch a galaxy die, and you witness one of the most gradual yet profound transformations in nature. The process begins when something disrupts the galaxy's gas supply. Maybe the galaxy falls into a dense cluster environment. Maybe it collides with another system. Maybe it simply exhausts its fuel after billions of years of star formation. Whatever the cause, the effect is the same. Star formation slows. The massive blue stars, which only live for 10 or 20 million years, begin dying without being replaced. Supernovas flash across the galaxy, each one marking the death of another blue giant. The galaxy's spectrum starts shifting. The intense ultraviolet light fades. The bright blue glow diminishes. Yellow and orange wavelengths become more prominent as the intermediate mass stars dominate. Eventually, even these stars age and cool, leaving only the small red dwarfs and the ancient red giants nearing the end of their lives. The entire galaxy takes on a reddish hue, the cosmic color of death. This transformation takes between 1 and 3 billion years, depending on how quickly the gas supply gets cut off. A galaxy that loses its gas suddenly, through violent stripping, might complete the transition in just a few 100 million years. A galaxy that slowly exhausts its supply through natural consumption takes longer, fading gradually like a dimming light bulb. But the endpoint is always the same: red light, old stars, silence. The Hubble Space Telescope has captured hundreds of galaxies at various stages of this process, creating a visual timeline of death. In the images, you can see galaxies that are still mostly blue with just hints of red at their cores. Others show half and half, blue outer regions with red centers, frozen in mid-transition. The fully dead systems appear as smooth, featureless ellipticals, glowing with the dull red light of stellar old age. These are the corpses, the final stage, the end point of galactic evolution in hostile environments. The scale of these galactic graveyards challenges human comprehension. The Coma Cluster alone contains more dead galaxies than all the living galaxies in our local group combined. Our local group, which includes the Milky Way, Andromeda, and about 80 smaller systems, represents a typical galactic neighborhood. Most of our neighbors are alive, forming stars, glowing with the light of youth and middle age. But in the Coma Cluster, the ratio reverses dramatically. For every living galaxy, there are 10 or 20 dead ones. The graveyard dwarfs the neighborhood. Multiply this across the universe, and the numbers become staggering. Astronomers estimate that approximately 30% of all galaxies in the observable universe are already dead. That's roughly 600 billion corpses floating through space, each one a system that once blazed with the light of billions of newborn stars, but now sits dark and silent, slowly fading. These dead zones aren't evenly distributed. They cluster in specific regions, particularly in massive galaxy clusters where environmental conditions turn hostile. The Perseus cluster, the Virgo cluster, the Fornax cluster, all of them show the same pattern. Dense concentrations of red, dead galaxies surrounded by sparse populations of blue, living systems at the periphery. The boundary between life and death in these regions is surprisingly sharp. Cross an invisible line moving inward toward the cluster core, and the survival rate plummets. Galaxies that were forming stars at healthy rates suddenly find themselves stripped, strangled, harassed. Within a billion years, most of them join the graveyard. The James Webb Space Telescope has pushed our view of galactic death back to cosmic dawn. When JWST began observing the most distant reaches of space, looking at light that has traveled for over 13 billion years, astronomers expected to find young, vigorous galaxies in their prime. Instead, they found graveyards. Even in the early universe, when the cosmos was barely a billion years old, massive clusters of dead galaxies already existed. These ancient graveyards prove that galaxy death has been happening since the universe's youth, that the mechanisms that kill galaxies were operating at full strength when the cosmos was less than 1/10 its current age. One particularly disturbing discovery involved a cluster of galaxies as they appeared just 1.4 billion years after the Big Bang. Most of the cluster members were already red and dead, their star formation shut down despite the universe being awash in gas and raw materials. Something killed these galaxies fast, stripping or consuming their fuel in just a few 100 million years. The discovery shattered previous theories suggesting galaxy death was a modern phenomenon, something that only became common as the universe aged and clusters grew denser. Instead, it appears that hostile environments capable of killing galaxies formed early and have been operating continuously for over 13 billion years. The graveyards we see in the local universe are just the latest additions to a cosmic cemetery that began filling shortly after the first galaxies formed. JWST's infrared capabilities allow it to see through the dust that obscures many of these distant dead zones, revealing their full extent for the first time. The data suggests that galaxy death might have been even more common in the early universe than it is today, that a larger percentage of ancient galaxies died young compared to modern populations. The distribution of galactic graveyards across the universe reveals an unsettling pattern. They're not random. They don't appear scattered evenly through space like stars in the night sky. Instead, they cluster in specific environments where physical conditions become hostile to star formation. The most common locations are the cores of massive galaxy clusters, where hundreds or thousands of galaxies pack into regions just a few million light-years across. In these dense environments, the space between galaxies fills with superheated gas at temperatures exceeding 10 million degrees. This intracluster medium creates a hostile atmosphere that strips gas from any galaxy passing through it. The second common location for graveyards is in and around galaxy groups, smaller collections of dozens of galaxies bound together by gravity. While less extreme than massive clusters, these groups still create environmental conditions harsh enough to kill some of their members, particularly smaller dwarf galaxies that lack the mass to hold on to their gas. The third location is more subtle and more disturbing. Astronomers have discovered filaments of dark matter connecting galaxy clusters, cosmic highways along which galaxies flow as they fall into larger structures. Galaxies traveling along these filaments often show signs of pre-processing, early stages of gas loss that occur before they even reach the main cluster. By the time they arrive at the cluster core, they're already dying. Their star formation rates crashed, their gas supplies depleted. The pattern is clear. Galactic graveyards form wherever galaxies congregate in large numbers, wherever gravity pulls systems together into dense concentrations that create hostile environmental conditions. The mechanism is environmental. The cause is crowding. The result is mass death. Scientists study these cosmic graveyards the way forensic investigators study crime scenes, looking for clues about what killed the victims and when. The techniques are remarkably similar. Astronomers analyze the stellar populations in dead galaxies to determine when star formation stopped, essentially determining the time of death. They study the distribution of elements within the galaxy to understand what processes were occurring before death. They map the velocity and position of corpses within the cluster to reconstruct how they arrived at their current locations. Each dead galaxy tells a story. An elliptical galaxy composed entirely of old red stars died billions of years ago, long before falling into its current cluster. A spiral galaxy with a red core but blue outer regions died recently, probably within the last billion years, and still retains its structural shape. A galaxy with disturbed morphology and tidal tails died violently, probably in a collision or through rapid stripping. The spectra of dead galaxies reveal their chemical compositions, showing which elements are present and in what abundances. This chemical fingerprint indicates what types of stars formed before death and how long ago those stars were born. Advanced computer simulations allow astronomers to run the clock backward, modeling how the galaxy's orbit might have evolved over billions of years, determining when it first entered hostile territory. The combination of observation and simulation creates a detailed picture of each galaxy's death. The circumstances, the timeline, the mechanism. In cluster after cluster, the forensic evidence points to the same conclusion. These galaxies were killed by their environment, murdered by the very structures they fell into. Three main mechanisms emerge from the forensic analysis, three ways that environments kill galaxies. The first is ram pressure stripping, a violent process where galaxies moving through hot intracluster gas experience headwinds that tear away their star-forming material like a hurricane stripping shingles from a roof. The second is strangulation, a slower death where galaxies get cut off from external gas supplies and slowly starve, consuming their remaining fuel with no way to replenish it. The third is harassment, high-speed encounters with other galaxies that don't result in mergers but gravitationally disturb gas supplies and trigger instabilities. These three mechanisms work together, sometimes simultaneously, to transform living galaxies into dead ones. A galaxy might first experience harassment as it falls into a cluster, disrupting its gas. Then, strangulation begins as the hot cluster environment prevents new gas from accreting onto the galaxy. Finally, ram pressure stripping tears away the remaining internal gas as the galaxy plunges through the dense cluster core. The combination is lethal. The timeline varies, but the outcome does not. Whether death takes 100 million years or 2 billion years, whether it comes through violent stripping or gradual starvation, the galaxy ends up in the same place. Red, dead, and floating through space as a corpse among corpses in the cosmic graveyard. Understanding these mechanisms matters because they tell us not just how galaxies die, but how our own galaxy might eventually die when the Milky Way and Andromeda merge and fall into larger structures. The graveyards are showing us our future, a preview of the fate that awaits every galaxy in regions where crowding turns environment deadly. Imagine sticking your hand out the window of a moving car. The faster you go, the stronger the wind pushes against your hand, forcing it backward. Now, scale that simple physics up to galactic proportions and replace air with superheated plasma at temperatures exceeding 10 million degrees. This is ram pressure stripping, the most violent mechanism for killing galaxies, and it's happening right now throughout the universe wherever galaxies plunge through the dense cores of massive clusters. The process is brutally simple. As a galaxy moves through the intracluster medium, the hot gas between galaxies it experiences a headwind. This isn't wind in any conventional sense. There's no air, no atmosphere, no molecules bumping into each other like weather on Earth. Instead, it's a pressure differential created by the galaxy's motion through an extremely thin but incredibly hot gas that fills the space between cluster members. The galaxy is moving, sometimes at speeds exceeding 1,000 kilometers per second. The intracluster gas is relatively stationary. The collision between the galaxy's internal gas and the external medium creates pressure on the leading edge of the galaxy. Pressure strong enough to overcome the galaxy's own gravity and tear gas away from its outer regions. Once this stripping begins, it accelerates rapidly, peeling away layer after layer of star-forming material until only the galaxy's stellar core remains, naked and stripped of the fuel needed to create new stars. The physics of ram pressure operates on principles that sound deceptively simple but manifest in terrifyingly destructive ways at cosmic scales. Ram pressure is the force exerted on a body moving through a fluid, calculated by multiplying the fluid's density by the square of the velocity. On Earth, you experience ram pressure every time you feel wind resistance while driving or cycling. The faster you move through air, which is a fluid, the greater the force pushing against you. At galactic scales, the fluid is the intracluster medium, a plasma so hot that electrons have been stripped from their atoms, creating a soup of charged particles. The temperature of this medium typically ranges from 10 million to 100 million degrees Kelvin, hot enough that it emits primarily in X-rays rather than visible light. Despite these extreme temperatures, the intracluster medium is incredibly diffuse, with densities around 1,000 times lower than the best laboratory vacuum we can create on Earth. Yet, when a galaxy plows through this near vacuum at speeds of 500 to 1,500 kilometers per second, the cumulative pressure builds to enormous levels. The ram pressure force scales with velocity squared, meaning a galaxy moving twice as fast experiences 4 times the stripping force. This relationship creates a critical threshold. Below certain speeds, a galaxy's gravity can hold onto its gas despite the external pressure. Above that threshold, the ram pressure overwhelms gravity and stripping begins. The temperature of the intracluster gas matters because hotter gas has higher pressure at the same density, increasing the stripping efficiency. In the hottest cluster cores, even galaxies moving at moderate speeds experience devastating gas loss. The most visually striking evidence of ram pressure stripping comes from objects astronomers call jellyfish galaxies, and the name is disturbingly appropriate. These systems look exactly like cosmic jellyfish drifting through space, with a bright head representing the galaxy's stellar core and long, flowing tentacles of stripped gas and stars trailing behind. The tentacles can stretch for hundreds of thousands of light years, longer than the diameter of the Milky Way, creating structures of haunting beauty and profound violence. The jellyfish shape forms because ram pressure doesn't strip gas uniformly. As the galaxy moves through the intracluster medium, pressure builds up on the leading edge while the trailing edge experiences lower pressure, like the wake behind a boat. Gas gets pushed backward, accumulating in streams and filaments that flow away from the galaxy in the direction opposite its motion. These streams remain visible because they contain dust and newborn stars that formed in the compressed gas as it was being stripped away. The result looks organic, alive almost, like a creature swimming through the cosmic ocean. But this is death in action, a galaxy being flayed alive, its vital organs exposed and torn away by forces it cannot resist. Dozens of jellyfish galaxies have been identified in various clusters, each one frozen in a different stage of the stripping process. Some show short, stubby tails indicating that stripping just began. Others display elaborate tentacles extending in multiple directions, suggesting complex orbital histories and varying ram pressure forces. The most extreme jellyfish galaxies have lost more than 90% of their original gas, with only tiny remnants clinging to the stellar core like the last drops of water on a wrung-out sponge. ESO 137001 represents perhaps the most spectacular and well-studied example of ram pressure stripping caught in the act. This spiral galaxy, located in the Norma cluster approximately 220 million light-years from Earth, is dying before our eyes, and we can measure exactly how fast it's happening. Observations across multiple wavelengths reveal the full horror of its destruction. In visible light, ESO 137001 appears as a tilted spiral with bright blue knots of star formation along its arms, looking almost normal at first glance. But in X-ray observations, the galaxy blazes with two enormous tails of hot gas streaming behind it for over 260,000 light-years. These tails glow at temperatures of 10 million degrees, heated by the compression and turbulence of the stripping process. Radio observations reveal cold molecular hydrogen being ripped away, the very fuel the galaxy needs for star formation. Ultraviolet observations show young stars forming in the tails, born in the stripped gas moments before it's lost forever. By combining data from all these wavelengths, astronomers calculated that ESO 137001 is losing gas at a rate of approximately 3 solar masses per year. This might not sound like much, but it's actually catastrophic. The galaxy currently contains about 1 billion solar masses of gas available for star formation. At the current stripping rate, all of that gas will be gone in approximately 300 million years. However, the rate is accelerating. As the galaxy penetrates deeper into the cluster core, ram pressure increases, the stripping becomes more efficient, and the death spiral accelerates. Recent models suggest ESO 137001 will be completely stripped, reduced to a red and dead elliptical galaxy, within just 100 million years from now. We're witnessing the final act of a multi-billion-year drama, watching a galaxy's last gasps as it loses everything that made it alive. Speed determines survival in the hostile environment of galaxy clusters. A galaxy drifting slowly through the intracluster medium might experience only minimal gas loss, manageable disruption that doesn't threaten its long-term star formation. But once velocities exceed a critical threshold, typically around 500 kilometers per second relative to the surrounding gas, stripping becomes inevitable and devastating. Most galaxies in dense cluster cores move much faster than this threshold. Orbital velocities in massive clusters like Coma regularly exceed 1,000 kilometers per second, with some galaxies racing through the intracluster medium at 1,500 kilometers per second or more. At these speeds, the ram pressure force becomes so intense that it overwhelms even the deepest gravitational wells. The relationship between speed and stripping efficiency is brutally exponential. A galaxy moving at 1,000 kilometers per second experiences ram pressure 4 times stronger than a galaxy at 500 kilometers per second, and 16 times stronger than a galaxy at 250 kilometers per second. This means that small changes in orbital velocity can spell the difference between life and death for a galaxy. Astronomers have observed cases where galaxies on highly elliptical orbits experience periodic stripping. As they plunge through the dense cluster core at high speed, ram pressure tears away their outer gas layers. Then, as they swing back out to the cluster periphery and slow down, the stripping temporarily stops, giving the galaxy a brief reprieve. But with each passage through the core, more gas is lost, and eventually nothing remains. The speed factor also explains why some galaxies in clusters survive while others die. Galaxies on stable circular orbits that keep them in the less dense outer regions can maintain lower velocities and avoid the worst stripping. Galaxies that fall directly into the cluster core on radial orbits hit peak ram pressure almost immediately and get stripped completely in a single catastrophic passage. Ram pressure stripping doesn't remove all of a galaxy's gas simultaneously. The process is selective, sequential, and cruel in its efficiency. It begins at the outermost edges where the gas is most loosely bound by gravity. The galaxy's gravitational pull weakens with distance from the center, following an inverse square law. Gas in the outer regions, sometimes extending hundreds of thousands of light years from the galactic core, feels only a weak gravitational tug and can be stripped away relatively easily. As this outer gas gets removed, ram pressure begins working on progressively deeper layers, peeling the galaxy like an onion. The cold neutral hydrogen that forms extended halos around spiral galaxies goes first, swept away like dust in a hurricane. Next, the molecular hydrogen in the outer disk gets stripped, removing the fuel supply for star formation in the galaxy's periphery. As stripping continues inward, it eventually reaches the main star-forming disk, where gas densities are higher and gravity holds on more tightly. Here, the process slows but doesn't stop. Particularly intense ram pressure can strip gas even from these well-protected central regions, though it takes longer and requires higher velocities. The very core of the galaxy, where gas densities peak and gravity is strongest, can sometimes retain small amounts of molecular gas even in the harshest environments. This creates the final stage of stripping where a galaxy becomes a naked stellar core surrounded by a tiny residual gas disk, just enough to maintain feeble star formation for a few 100 million more years before even that disappears. The selectivity of stripping creates a characteristic signature. Stripped galaxies show truncated gas disks that end abruptly, rather than fading gradually like normal spirals. They display one-sided star formation, with new stars forming only on the side sheltered from ram pressure, while the exposed side remains dark and dormant. Their stellar disks remain intact because stars, unlike gas, are gravitationally bound tightly enough that ram pressure cannot remove them. The result is a galaxy that looks normal in visible light but appears mutilated in radio and ultraviolet observations. A corpse that still wears the face of life. The long tails of stripped gas trailing behind jellyfish galaxies harbor one of the most bizarre and poignant phenomena in astrophysics. New stars are forming in these tails, born in gas that's being ripped away from their parent galaxy and will never return. These are orphan stars, created in the moment of destruction, doomed to spend their entire lives drifting through intergalactic space far from any galaxy. The formation mechanism is almost paradoxical. As gas gets stripped and flows backward away from the galaxy, it experiences compression and turbulence. This compression can trigger the collapse of gas clouds, igniting star formation in the stripped material. Observations of jellyfish galaxies show bright blue knots scattered throughout the tails, each knot representing a cluster of young, massive stars less than 10 million years old. Some tails contain hundreds of these star-forming regions, collectively creating thousands or even millions of new stars. The irony is profound. RAM pressure stripping, the process killing the galaxy, is simultaneously creating one last generation of stars in the debris field it leaves behind. But these stars will never contribute to their parent galaxy. They're forming in gas that's already escaped the galaxy's gravitational pull, flowing away at speeds of hundreds of kilometers per second. By the time these stars mature, they'll be millions of light years from their birthplace, scattered across intergalactic space as isolated wanderers. Computer simulations show that many of these orphan stars will eventually be captured by other galaxies, becoming permanent residents of foreign systems. Others will drift alone through the void between clusters, solitary outcasts that began life in a moment of violent destruction. The orphan stars raise disturbing questions about galactic citizenship. If a significant fraction of a galaxy's star formation occurs in stripped tails rather than in the main disk, how do we define where the galaxy ends and intergalactic space begins? Are these stars part of the galaxy that spawned them, or part of the intracluster population? The question isn't merely philosophical. Understanding where stars form and where they ultimately reside affects our calculations of galactic mass, cluster mass, and the distribution of matter throughout the universe. Observing RAM pressure stripping requires looking at galaxies across multiple wavelengths simultaneously because different wavelengths reveal different aspects of the violence unfolding. X-ray observations show the hot intracluster medium that creates RAM pressure, appearing as diffuse emission filling the space between galaxies. They also reveal shocked hot gas in the stripped tails where compression has heated material to millions of degrees. The Chandra X-ray Observatory has captured dozens of examples, showing bright X-ray tails trailing behind galaxies as they plow through cluster cores. Optical observations reveal the stellar content and ongoing star formation, showing where young blue stars are forming in response to gas compression. The Hubble Space Telescope's optical images of jellyfish galaxies display spectacular detail, resolving individual star-forming regions in the tails and showing how stellar populations differ between the galaxy core and stripped material. Radio observations trace a cold, neutral, and molecular hydrogen, the raw fuel for star formation, revealing exactly which gas reservoirs are being stripped and at what rates. Radio telescopes like ALMA and the VLA have mapped the molecular gas in stripped galaxies, showing that even dense molecular clouds, which should resist stripping, are being torn away in the most extreme cases. Ultraviolet observations identify the youngest, hottest stars, revealing where star formation occurred most recently. These newborn stars serve as markers, showing where gas was located in the recent past, typically less than 10 million years ago. By combining all these wavelengths, astronomers build a complete picture of the stripping process, seeing not just the current state but reconstructing the recent history and predicting the future trajectory. The multi-wavelength approach has revealed that RAM pressure stripping operates more efficiently than theoretical models predicted. In the worst environments, galaxies can lose their entire gas supply in under 100 million years, far faster than the billion-year timescales previously assumed. Once RAM pressure stripping begins in earnest, the galaxy's fate is sealed, though the timeline to complete death varies depending on orbital trajectory and initial gas content. A typical spiral galaxy falling into a massive cluster core will experience first contact with significant RAM pressure when it crosses into the inner cluster, usually within about 1 million light-years of the center. At this point, stripping of outer gas layers begins immediately. Over the next 100 to 300 million years, the galaxy loses its extended gas halo and outer disk material as it makes its first plunge through the dense intracluster medium. If the orbit is elliptical, the galaxy may swing back out to less dense regions, experiencing a temporary reprieve where stripping slows or stops for perhaps 200 million years before the next pass through the core. With each subsequent passage, more gas is stripped until the galaxy's orbit decays and it settles into the cluster core permanently. The final stripping phase, where the last molecular gas gets removed from the central disk, typically takes another 100 to 200 million years. From first contact to complete gas exhaustion, the total timeline ranges from as little as 100 million years for galaxies on radial orbits that fall straight into the densest regions, to perhaps 500 million years for galaxies on more gradual orbital paths. These timescales are instantaneous compared to the multi-billion-year ages of galaxies, representing just 1 to 5% of a typical galaxy's lifetime. The brief duration makes catching galaxies in the act of being stripped relatively rare, explaining why jellyfish galaxies constitute only about 1 to 2% of cluster populations in surveys. Most galaxies are either not yet stripped or already dead, having completed the process billions of years ago. There comes a point of no return, a threshold beyond which a galaxy cannot recover even if it somehow escapes the hostile environment that's killing it. This critical threshold occurs when the galaxy has lost roughly 50 to 70% of its initial cold gas supply. Once gas loss exceeds this level, several irreversible processes take effect. First, the galaxy's gravitational potential changes. With less gas mass contributing to the overall gravitational well, the galaxy's ability to attract new gas diminishes, making any future gas accretion much less efficient. Second, the star formation rate collapses below the level needed to maintain a healthy stellar population. Galaxies need to form at least a few solar masses of stars per year to remain vibrant. Below this threshold, the remaining star formation becomes sporadic and insufficient. Third, the galaxy's morphology begins transforming irreversibly. As outer gas layers are stripped, the disk thins and contracts. The spiral arms, which are sustained by ongoing star formation and gas dynamics, begin fading. Within a billion years, even if no additional stripping occurs, the galaxy will complete its transformation to a red elliptical through simple exhaustion of its remaining fuel. Studies of galaxies that have escaped cluster cores, perhaps through gravitational interactions with other clusters or unusual orbital dynamics, show that this point of no return is real and unforgiving. Galaxies that lost only 30 to 40% of their gas before escaping can recover, slowly reaccreting material from their surroundings and restarting star formation. But galaxies that lost more than half their gas remain dead even billions of years after leaving the hostile environment, their star formation permanently extinguished despite no longer experiencing ram pressure. They're the walking dead, galaxies that died years ago, but whose stellar corpses still shine with the light of stars born before the killing began, cruising through space as permanent monuments to the power of ram pressure stripping. Not all galaxy deaths are violent. While ram pressure stripping tears gas away in spectacular displays of cosmic destruction, another mechanism kills just as effectively through patience and deprivation. This is strangulation, and it's arguably more insidious than stripping because the galaxy dies from the inside out, slowly consuming its own reserves with no way to replenish them. Imagine being locked in a room with a limited food supply and no way to get more. You can see the food outside, you know it exists, but you cannot reach it. Eventually, inevitably, you consume everything available and starve. This is what happens to strangled galaxies. The process begins when a galaxy enters an environment that cuts off its access to external gas supplies. Every galaxy, including the Milky Way, exists within an extended halo of hot, diffuse gas that stretches far beyond the visible stellar disk. This circumgalactic medium serves as a reservoir, a cosmic pantry from which the galaxy draws fresh material to sustain star formation over billions of years. Gas from this halo slowly cools and falls onto the galaxy's disk, replenishing what gets consumed by star formation and stellar winds. In a healthy, isolated galaxy, this accretion process continues indefinitely, maintaining a steady supply of fuel that allows star formation to persist for 10 billion years or more. But when a galaxy falls into a dense cluster environment, the hot intracluster medium heats and strips away this extended gas halo. The galaxy's external reservoir disappears, severed cleanly from the main body like cutting a lifeline. The galaxy itself remains intact, its disk gas untouched, but the replenishment mechanism stops working. From that moment forward, the galaxy lives on borrowed time, consuming its internal gas supply with no way to acquire more. The removal of a galaxy's hot gas halo happens through thermal and hydrodynamic processes that are less visually dramatic than ram pressure stripping, but equally lethal in their consequences. When a galaxy first enters a cluster environment, its extended hot gas halo encounters the even hotter intracluster medium. The boundary between these two gas reservoirs becomes thermally unstable. The intracluster gas, at temperatures of 10 to 100 million degrees, is significantly hotter than the galaxy's halo gas, which typically sits around 1 to 2 million degrees. This temperature differential creates pressure imbalances that drive mixing and evaporation. The cooler halo gas gets heated through thermal conduction and turbulent mixing, its temperature rising until it becomes indistinguishable from the surrounding intracluster medium. Once heated to these extreme temperatures, the gas can no longer cool and fall onto the galaxy's disk. It's been effectively stolen, absorbed into the cluster's gas reservoir, and lost forever to the galaxy that brought it. This process, sometimes called thermal evaporation, operates over timescales of several hundred million years. Unlike ram pressure stripping, which removes gas through direct pressure, thermal evaporation works through energy transfer, cooking the galaxy's gas supply until it becomes too hot to be useful. The removal is complete and irreversible. X-ray observations of galaxies in clusters show this process clearly. Isolated galaxies display extended X-ray halos of hot gas surrounding their stellar disks. Cluster galaxies show truncated halos or no extended X-ray emission at all, their gas reservoirs stripped away by the hostile thermal environment. The galaxy's disk gas remains temporarily safe because it's colder and denser, protected by its own gravity and shielded by the stellar disk. But without the external halo to provide fresh fuel, that disk gas becomes a non-renewable resource, a finite supply that will eventually run out. The starvation timeline unfolds over 1 to 2 billion years, making it one of the slower forms of galaxy death, but no less certain. Once a galaxy's gas supply gets cut off, star formation continues for a while, business as usual. The galaxy doesn't immediately realize it's been sentenced to death. It keeps forming stars at whatever rate its current gas supply supports, typically a few solar masses per year for a Milky Way-sized spiral. But now, every star that forms permanently depletes the remaining fuel. Every solar mass of gas converted into stars is gone forever, with no replenishment flowing in from the external halo. Do the math and the timeline becomes clear. A typical spiral galaxy entering a cluster might contain about 10 billion solar masses of cold gas available for star formation. If that galaxy forms stars at a rate of 3 solar masses per year, the gas supply lasts approximately 3 billion years. However, the calculation isn't quite that simple. As the gas supply diminishes, star formation becomes less efficient. Less gas means fewer giant molecular clouds, which means fewer sites where stars can form. The star formation rate doesn't remain constant, but gradually declines as the galaxy consumes its dwindling reserves. Additionally, massive stars that form early in this process explode as supernovas, heating and ejecting some of the remaining gas, which further reduces the usable supply. When you account for these factors, the realistic starvation timeline for a cluster galaxy drops to between 1 and 2 billion years. This might sound like a long time, and it is by human standards. But remember that galaxies live for 10 billion years or more under normal conditions. Strangulation cuts their lifespan short, killing them when they should still be in their prime. The process is gradual enough that each generation of stars forms normally, unaware that they're part of a dying system. Only when we step back and observe the galaxy over cosmic timescales does the tragedy become apparent. The observable stages of strangulation create an evolutionary sequence that astronomers can trace by observing many galaxies at different points in the process. Stage 1 is a blue spiral galaxy that has just entered the cluster and lost its external gas halo but still retains all of its disk gas. This galaxy looks completely healthy, actively forming stars throughout its spiral arms, showing no obvious signs of impending doom. Only detailed measurements of its extended gas halo, or lack thereof, reveal that death has already begun. Stage 2 emerges a few 100 million years later when the star formation rate begins declining measurably. The galaxy still appears blue, but careful spectral analysis shows that star formation has dropped by perhaps 20 to 30% from its previous peak. The outer spiral arms start looking less defined as star formation in those regions becomes sporadic. Stage 3 represents the midpoint of starvation, typically reached about 500 million to 1 billion years after strangulation began. Now, the galaxy shows clear signs of decline. The outer regions have turned red, as the massive blue stars there have died without replacement. Star formation concentrates in the inner disk, where the remaining gas supply has contracted. The galaxy takes on a blue center, red outskirts appearance that marks it as a dying system. Stage 4 is the red spiral phase, reached between 1 and 1.5 billion years into the starvation process. The galaxy has consumed nearly all its gas. Only a small reservoir remains in the very core, supporting feeble star formation at rates below half a solar mass per year. Most of the stellar population is now old and red, though the spiral structure remains visible, traced by dust lanes and the positions of long dead stars. Stage 5 is the final transformation into a red elliptical galaxy, completed between 1.5 and 2 billion years after strangulation started. All gas is gone, all star formation has ceased, and the spiral structure has faded or been destroyed by gravitational interactions. What remains is a smooth, elliptical galaxy filled with ancient stars. A corpse that will fade slowly over trillions of years with no possibility of revival. This evolutionary sequence plays out differently for different galaxies depending on their initial gas content and star formation rates, but the stages and the inevitable endpoint remain the same. Galaxy harassment introduces additional complexity to the strangulation process, accelerating death through gravitational disturbances that wouldn't occur in isolation. Harassment refers to high-speed encounters between galaxies that pass close to each other without merging. In dense cluster environments where hundreds of galaxies orbit the same gravitational center, these close encounters happen frequently. Two galaxies might pass within a few 100,000 light-years of each other at relative speeds of 1,000 kilometers per second. The encounter lasts only a few million years, far too brief for the galaxies to merge or even gravitationally capture each other. But those few million years are enough to cause significant damage. The gravitational interaction during the encounter creates tidal forces that disturb the gas in both galaxies. Gas clouds get pulled toward the other galaxy and then snap back when the galaxies separate, creating turbulence and heating throughout the disk. Some gas gets flung out of the galaxy entirely, ejected by the gravitational slingshot effect. The disturbance also disrupts the orderly rotation of gas in the disk, making it harder for gas clouds to collapse and form stars efficiently. A single harassment encounter might remove or heat 5 to 10% of a galaxy's cold gas supply, and might reduce star formation efficiency by 20 to 30% for a few 100 million years after the encounter. That alone wouldn't be catastrophic. A galaxy could recover from one harassment event. But in dense cluster cores, galaxies don't experience just one encounter. They experience dozens over the course of their orbital lifetime. Each encounter strips away a little more gas, creates a little more turbulence, reduces star formation efficiency a little more. The effects are cumulative and eventually devastating. The cumulative damage from repeated harassment can actually exceed the damage from a single major collision. Consider two scenarios. In the first, a galaxy experiences a direct collision with another galaxy of similar mass, a major merger that completely destroys both systems and creates a new elliptical galaxy. This is violent and transformative, but happens only once. In the second scenario, a galaxy experiences 20 harassment encounters over 2 billion years, each one causing relatively minor damage. After the first few encounters, the galaxy still looks healthy. After 10 encounters, it's showing signs of stress, reduced star formation, some gas loss, disrupted morphology. After 20 encounters, the galaxy is barely functioning. Its gas supply is heavily depleted through multiple small losses. Its disk structure is warped and asymmetric from repeated gravitational tugging. Its star formation rate has crashed because the constant disturbances prevent gas clouds from collapsing efficiently. The galaxy ends up just as dead as it would have from a major merger, but it took longer to get there and the process was more insidious. Computer simulations of cluster environments confirm this cumulative harassment effect. When simulated galaxies fall into clusters, those experiencing frequent harassment die faster than those following orbits that minimize close encounters with neighbors. The harassment accelerates strangulation by removing gas that would otherwise sustain star formation for longer, and by heating and disrupting gas that remains, making it less able to form stars even while it's still present. This is death by 1,000 cuts. each harassment encounter representing another wound that weakens the galaxy until it can no longer survive. Anemic galaxies represent a distinct phase in the starvation process, systems that have lost most of their gas but haven't quite died yet. These galaxies, first identified in the Virgo cluster during systematic surveys in the 1970s, show peculiar properties that mark them as living on the edge of death. An anemic galaxy looks like a spiral at first glance, with visible spiral arms and a rotating disk structure. But closer examination reveals profound abnormalities. The star formation rate is drastically suppressed, often by a factor of 5 to 10 compared to similar galaxies in isolated environments. A spiral that should be forming 10 solar masses of stars per year is forming only 1 or 2. The gas content is depleted, with 50 to 80% of the expected gas missing compared to healthy spirals. What gas remains is mostly concentrated in the inner disk, with the outer regions already swept clean. The spiral arms are present but faint, traced more by dust lanes than by bright young stars. The overall appearance is washed out, faded like a photograph left too long in the sun. These are galaxies in the late stages of strangulation, clinging to life with the last remnants of their fuel supply. They're still forming stars, which technically makes them alive, but at rates so low they're essentially zombies going through the motions while decay continues inexorably. The anemic phase typically lasts between 200 and 500 million years, bridging the gap between healthy blue spirals and dead red ellipticals. During this phase, the galaxy continues consuming its remaining gas at a reduced rate while stellar populations age and the overall color shifts steadily toward red. Anemic galaxies are particularly common in the outer regions of clusters and in galaxy groups, intermediate density environments where strangulation operates efficiently, but RAM pressure stripping is too weak to tear gas away violently. These galaxies are dying slowly, starving in plain sight, and their presence in large numbers throughout clusters and groups proves that strangulation is one of the primary mechanisms for building the galactic graveyards. Color gradients within dying galaxies tell the story of strangulation with striking clarity. A healthy star-forming spiral galaxy shows a relatively uniform color across its disk, perhaps slightly bluer in the spiral arms, where young stars concentrate but without dramatic variations. A strangled galaxy in mid-death displays a characteristic pattern of blue center and red outskirts that immediately marks it as a system running out of gas. The physics behind this pattern is straightforward. Star formation in a dying galaxy retreats inward as the gas supply dwindles. The outer disk loses its gas first, either through consumption in star formation or through weak stripping and heating at the galaxy's edges. Once the outer regions run out of gas, star formation there ceases. The massive blue stars that populated those regions die within 10 to 20 million years, leaving only the longer-lived red and yellow stars. The outer disk turns red, the cosmic color of death, while the center remains blue because gas still exists there to fuel ongoing star formation. As starvation continues, the blue region shrinks. What started as a blue center covering the inner half of the galaxy contracts to the inner third, then the inner quarter. Eventually, even the center turns red when the last gas gets consumed. The color gradient serves as a visual timeline showing how far the death process has advanced. Galaxies with only slightly red outskirts are early in starvation, perhaps a few 100 million years into the process. Galaxies with red outskirts and small blue cores are in late stages, within a few 100 million years of complete death. Galaxies that are red throughout have finished dying, their starvation complete. Measuring these color gradients across large samples of cluster galaxies allows astronomers to construct detailed models of the strangulation timeline, determining how quickly galaxies die and what factors accelerate or slow the process. The gradients also provide a way to identify dying galaxies in distant clusters where we cannot measure gas content directly, making them a valuable diagnostic tool for studying galaxy death across cosmic history. Comparing strangulation to ram pressure stripping reveals two fundamentally different approaches to killing galaxies, yet both lead to the same endpoint. Ram pressure is violent, fast, and visually spectacular. It tears gas away from the outside in, leaving long tails of stripped material that can be observed across multiple wavelengths. The process completes in 100 to 500 million years, killing galaxies in what amounts to a cosmic instant. Strangulation is gentle, slow, and nearly invisible. It cuts off gas supplies without removing what's already present, allowing the galaxy to consume itself from the inside out over 1 to 2 billion years. Ram pressure creates jellyfish galaxies with disturbed morphologies and obvious signs of trauma. Strangulation creates anemic galaxies that look superficially normal but are slowly fading away. Despite these dramatic differences in method and timeline, the outcome is identical. Both mechanisms remove the galaxy's ability to form stars. Both transform blue spirals into red ellipticals. Both create the same type of corpse to populate the galactic graveyards. The key difference lies in what happens to the gas. In ram pressure stripping, the gas is removed but not destroyed. It ends up in the intracluster medium, or forming orphan stars in stripped tails, redistributed but still present in the cluster. In strangulation, the gas gets converted into stars within the dying galaxy itself. The galaxy consumes its own flesh, transforming its remaining fuel into one last generation of stars that will slowly age and redden. This difference has implications for understanding how matter distributes itself in clusters over cosmic time. Stripped galaxies contribute their gas to the intracluster medium, enriching it with metals and increasing its mass. Strangled galaxies lock their remaining gas into stars, keeping it bound to the galaxy. Over billions of years, these different pathways affect how much mass ends up in galaxies versus the space between galaxies, influencing cluster evolution and the formation of new structures. What determines whether a galaxy experiences violent ram pressure stripping or slower strangulation depends primarily on two factors: the density of the intracluster medium and the galaxy's orbital trajectory through the cluster. In the densest cluster cores, where the intracluster gas reaches its highest temperatures and pressures, ram pressure stripping dominates. Any galaxy passing through these regions at typical orbital velocities will experience stripping regardless of other factors. The ram pressure force simply overwhelms the galaxy's gravity, tearing gas away in a process that begins immediately and proceeds rapidly. These core regions represent perhaps 10 to 20% of the cluster volume, but account for the majority of violent stripping events. Moving outward from the core, the intracluster medium becomes less dense and ram pressure weakens. In these intermediate regions, orbital trajectory matters more. A galaxy on a radial orbit that plunges through the cluster at high speed might still experience significant ram pressure stripping even in moderately dense environments. A galaxy on a more circular orbit that maintains lower velocities and stays in the outer cluster regions will experience primarily strangulation, with ram pressure playing only a minor role. The galaxy's own properties also influence which death mechanism dominates. Massive galaxies with deep gravitational wells can resist ram pressure stripping more effectively than small dwarf galaxies. A giant spiral might experience only strangulation in environments where a dwarf would be completely stripped. Gas-rich galaxies with large extended halos present more material to be stripped, making ram pressure more efficient. Gas-poor galaxies with compact distributions favor strangulation because there's less material for ram pressure to grab onto. In practice, many cluster galaxies experience both mechanisms simultaneously or sequentially. A galaxy might fall into a cluster and first experience strangulation as its extended gas halo gets thermally evaporated. Then, as it plunges toward the cluster core, ram pressure stripping tears away whatever disk gas remains. The combination kills faster than either mechanism alone, which explains why galaxies in the densest cluster cores die so quickly. Death is supposed to be permanent. In the cosmic graveyard, where hundreds of galaxies lie cold and lifeless, their star formation extinguished billions of years ago, we expect silence. We expect the slow fade as ancient stars burn through their remaining fuel and wink out one by one over trillions of years. What we don't expect is resurrection. Yet that's exactly what astronomers have discovered scattered throughout the universe. Dead galaxies, systems that stopped forming stars billions of years in the past, are suddenly coming back to life. These zombie galaxies are igniting new bursts of star formation after spending eons as cosmic corpses, defying every model of galaxy evolution and forcing scientists to confront an uncomfortable truth. Galaxy death is not always permanent, at least not immediately. The first hints of this phenomenon emerged from deep surveys of distant galaxy clusters conducted in the early 2000s. Astronomers noticed anomalous galaxies that showed all the characteristics of ancient red ellipticals, the classic dead galaxy morphology, but with small patches of bright blue stars embedded in their cores. The colors didn't make sense. A truly dead galaxy should be uniformly red, filled only with old stars that have been aging for billions of years. The presence of young blue stars, which live for only 10 to 20 million years, indicated that star formation had occurred recently. But how could a dead galaxy suddenly restart star formation? Where did the gas come from? The galaxies were clearly in hostile cluster environments, the same environments that killed them in the first place. The discovery was initially dismissed as observational error, or perhaps contamination from foreground objects. Then more examples appeared, and more. Eventually, the pattern became undeniable. Approximately 5 to 10% of dead galaxies in clusters show evidence of recent star formation, brief episodes of revival that occur long after the galaxy's supposed death. Cosmos Aztec 1 stands as perhaps the most dramatic and well-documented example of galactic resurrection. This massive elliptical galaxy, located approximately 9.5 billion light-years from Earth, presents a timeline that seems impossible, yet is confirmed by multiple independent observations. The galaxy formed early in cosmic history, building a large population of stars during the universe's youth when gas was plentiful and star formation rates throughout the cosmos were at their peak. Then, approximately 11 billion years ago, when the universe was just 3 billion years old, Cosmos Aztec 1's star formation shut down completely. Something removed its gas supply or made that gas unavailable for star formation. The galaxy went dark, its remaining massive stars dying out within a few tens of millions of years, leaving only the longer-lived red and yellow stars to carry the stellar population forward. For the next 2 billion years, Cosmos Aztec 1 remained dead. No new stars formed. No bright blue stellar populations appeared. The galaxy existed as a red elliptical, indistinguishable from billions of other cosmic corpses scattered throughout the universe. Its stellar population aged steadily. Its color shifted toward deeper red as even the yellow stars began fading, and by all appearances, it had reached its final state. Then, approximately 9 billion years ago, something extraordinary happened. Cosmos Aztec 1 suddenly exploded with star formation, igniting new stellar populations at a rate of approximately 800 solar masses per year. This is not a modest revival. This is one of the most intense starburst events ever observed, comparable to the star formation rates seen in major galaxy mergers. The burst lasted for perhaps 100 to 200 million years, creating billions of new stars before shutting down again. Today, we observe Cosmos Aztec 1, as it appeared 9.5 billion years ago due to light travel time, frozen in the midst of its resurrection. The galaxy shows the characteristic zombie signature, an ancient red stellar population surrounding a bright blue core where the recent starburst occurred. What caused this galaxy to come back from the dead after 2 billion years of dormancy remains one of the most puzzling questions in modern astrophysics. Several mechanisms can potentially resurrect dead galaxies, though none of them seem capable of explaining the most extreme cases like Cosmos Aztec 1. The most straightforward resurrection mechanism involves minor mergers, where a small gas-rich dwarf galaxy falls into the dead system and gets cannibalized. The dwarf's gas, stripped away by tidal forces during the interaction, funnels into the center of the larger galaxy where it can fuel a new burst of star formation. This process is well documented in the local universe, and can definitely restart star formation in otherwise dead systems. However, the gas supply from a dwarf galaxy merger is limited. A typical dwarf might contain a few 100 million to perhaps 1 billion solar masses of gas. That's enough to support star formation for 100 to 500 million years at modest rates, but not enough to explain the intense starbursts seen in some zombie galaxies. A second mechanism involves accretion from cosmic filaments, the vast streams of gas and dark matter that connect galaxy clusters across the universe. Even dead galaxies and clusters might occasionally pass through or near these filaments, potentially capturing fresh gas from the large-scale structure of the cosmos. This mechanism is theoretically possible, but observationally difficult to confirm. We cannot directly observe the cold gas in cosmic filaments at the distances where most zombie galaxies are found, making it impossible to verify whether filament accretion is actually occurring. The third, and perhaps most intriguing mechanism, involves previously hidden cold gas reservoirs within the galaxy itself. Some models suggest that dead galaxies might retain small amounts of molecular gas in their cores, gas that remained too cold and dense to be stripped or heated when the galaxy first died. This gas might sit dormant for billions of years in a stable equilibrium, neither forming stars nor being removed. Then some perturbation, perhaps a minor gravitational interaction or an instability in the gas distribution, triggers collapse and star formation. The gas was always there, just hidden and inactive. This mechanism explains why some zombie galaxies show no evidence of recent mergers or external gas accretion, but it requires that the hidden gas remain stable and unused for impossibly long periods. The tragedy of zombie galaxies lies in the temporary nature of their resurrection. These brief returns to life never last, because the fundamental conditions that killed the galaxy initially have not changed. If a galaxy died from strangulation because cluster environment cut off its external gas supply, that environment still exists. If it died from ram pressure stripping because it's moving through hot intracluster gas, that hostile medium remains. The resurrection provides only a temporary reprieve, a final gasp before permanent death. Consider a zombie galaxy that comes back to life through a minor merger that adds 500 million solar masses of fresh gas. If that galaxy forms stars at a rate of 5 solar masses per year, the new gas supply lasts only 100 million years. That sounds substantial until you remember that this galaxy spent the previous 2 billion years dead and will spend the next 10 billion years dead after this brief revival. The resurrection represents less than 1% of the galaxy's total lifetime, a blip that barely registers on cosmic timescales. Moreover, the hostile environment that killed the galaxy originally works to kill it again, often more efficiently the second time. If the galaxy is in a cluster core, ram pressure stripping immediately begins removing whatever new gas appeared, accelerating the consumption rate. If the galaxy experienced strangulation, any external gas halo the minor merger might have provided gets evaporated by the hot intracluster medium within a few 100 million years. The zombie is living on borrowed time from the moment of resurrection, and that borrowed time is short. Observations of zombie galaxies at various stages of their second lives show this clearly. Some are in full starburst mode, forming stars at peak rates while their new gas supply remains fresh. Others show declining star formation as the gas runs low. A few appear to be dying again, their second generation of blue stars already fading while the underlying red population reasserts dominance. The cycle from resurrection to second death takes typically between 100 and 500 million years, after which the galaxy returns to its previous red and dead state with no remaining possibility of revival. The permanent second death occurs faster than the first death, because zombie galaxies typically have less gas to work with during their revival, and because they're deeper in hostile environments by the time resurrection occurs. A galaxy might fall into a cluster and die over 1 billion years through strangulation as it gradually consumes its large initial gas supply. That dead galaxy drifts through the cluster for another billion years before experiencing a minor merger that provides perhaps 1/10 the gas it originally contained. Now, when star formation restarts, the limited fuel depletes rapidly. Additionally, the galaxy is probably deeper in the cluster core by this point in its orbital evolution, meaning ram pressure stripping and thermal evaporation work more efficiently against the new gas supply. The galaxy might have survived 1 billion years during its first death, but survives only 200 million years during its second death. Some zombie galaxies show evidence of experiencing multiple resurrections, dying, and being revived 2 or even 3 times before finally dying permanently. Each resurrection is shorter and less vigorous than the last as the available gas supplies diminish, and the hostile environment becomes more effective at killing the galaxy quickly. By the third or fourth death, the galaxy has exhausted all possible revival mechanisms. No dwarf galaxies remain nearby to merge with. All hidden gas reservoirs have been found and consumed. The The galaxy has drifted too far from cosmic filaments to accrete fresh material from large-scale structure. At this point, death becomes truly permanent. The galaxy will remain red and dead for the rest of cosmic history, slowly fading over trillions of years with no possibility of ever forming stars again. The final death comes not with drama, but with quiet exhaustion, the galaxy having literally run out of options for acquiring new fuel. Surveys of dead galaxies in various clusters suggest that approximately 5 to 10% show signs of recent or ongoing resurrection at any given time. This might sound like a small fraction, but it represents tens of millions of zombie galaxies across the observable universe. The percentage varies with environment. In the densest cluster cores where RAM pressure stripping is most intense, the zombie fraction drops to perhaps 2 to 3%, because any gas that appears gets stripped away so quickly that resurrection barely has time to occur. In less dense cluster regions and in galaxy groups, the zombie fraction rises to 10 to 15% because hostile environmental effects are weaker, allowing resurrections to last longer and be more easily detected. The zombie fraction also varies with cosmic time. Observations of distant clusters seen as they appeared billions of years ago show higher zombie fractions than nearby clusters. This makes sense given that the universe was denser in the past, with more gas available in cosmic filaments and more dwarf galaxies that could merge with dead systems. The zombie phenomenon was probably more common in the early universe when dead galaxies had more opportunities for resurrection. As the universe continues expanding and galaxies become more isolated, the zombie fraction will decrease. 10 billion years from now, the zombie fraction might drop to 1% or less as dead galaxies exhaust all possible revival mechanisms. And cosmic expansion reduces the frequency of interactions that could provide new gas. The fact that we observe zombies preferentially in the early universe tells us this is a transient phenomenon, common for a few billion years after cluster formation, but becoming increasingly rare as cosmic evolution proceeds and environments become more hostile. Zombie galaxies matter because they fundamentally complicate our models of galaxy evolution in several important ways. First, they break the simple one-way progression from blue spiral to red elliptical that dominated galactic evolution theory for decades. The classic model assumed that once a galaxy turned red and stopped forming stars, it remained dead forever. Observations of zombies prove this assumption wrong. Galaxy evolution is not a one-way street but can include reversals, multiple cycles of death and resurrection before final permanent death. Second, zombie galaxies affect our interpretation of galaxy colors and star formation histories. When we observe a red galaxy with a small blue core, we might be seeing a zombie in the midst of resurrection, not a normal star-forming galaxy. This misidentification can throw off statistical studies of star formation rates across cosmic time if we don't account for the zombie population separately. Third, zombies complicate our understanding of when and how galaxies die. If 5 to 10% of dead galaxies experience resurrection, then some fraction of currently red galaxies will become temporarily blue again in the future. This means our census of dead galaxies at any given time underestimates the total number of permanent deaths, while overestimating the number of healthy star-forming systems. Fourth, zombie galaxies reveal that death is not a binary state, but a complex process that can include multiple stages, dormant periods, and brief revivals. This challenges the classification schemes astronomers use to categorize galaxies as living or dead, active or passive. Perhaps we need a third category for galaxies that are technically dead but retain the capacity for resurrection under the right circumstances. The existence of zombies forces us to think about galaxy death more carefully, acknowledging that the process is messier and more complicated than our simplified models suggest. Identifying zombie galaxies requires looking for specific observable signatures that distinguish them from normal star-forming galaxies or truly dead systems. The most obvious signature is the color pattern, a predominantly red stellar population with small blue regions indicating recent star formation. However, this pattern alone is not conclusive because some normal galaxies show similar colors for different reasons. More definitive evidence comes from detailed spectral analysis that can date stellar populations precisely. Zombie galaxies show two distinct populations with very different ages. The bulk of stars are ancient, often 10 to 12 billion years old, formed during the galaxy's initial star-forming phase. Then there's a much younger population, typically less than a few 100 million years old, formed during the recent resurrection. The age gap between these populations is the smoking gun. A normal star-forming galaxy shows continuous star formation across many ages. A zombie shows a huge gap where no stars formed for billions of years between the old and young populations. This gap is visible in the spectrum through careful analysis of stellar absorption lines and chemical abundances. Young stars have different chemical compositions than old stars because the universe's metallicity has increased over time as successive generations of stars produce and disperse heavy elements. The young stars in zombie galaxies show enriched chemical compositions consistent with recent formation, while the old stars show primitive compositions consistent with formation in the early universe. Another observable signature involves the spatial distribution of young versus old stars. In zombie galaxies, young stars almost always concentrate in the very center where fresh gas presumably accumulated, while old stars dominate everywhere else. This is different from normal spiral galaxies, where young stars appear throughout the disk in spiral arms. The highly concentrated distribution of young stars in zombies suggests that whatever gas triggered the resurrection funneled directly to the galactic core rather than spreading throughout the system. The final, permanent death of zombie galaxies happens when all possible gas sources are exhausted and environmental conditions prevent any future gas acquisition. For a zombie galaxy deep in a cluster core, this permanent death is virtually guaranteed. Once the resurrection gas gets consumed, there's no mechanism to bring the galaxy back again. Any dwarf galaxies that might have merged with it have already been accreted. Any hidden internal gas reservoirs have been found and converted into stars. The galaxy is too far from cosmic filaments to capture new material from large-scale structure. The hot, dense intracluster medium prevents any external gas from cooling and falling onto the galaxy. At this point, the galaxy has truly reached its endpoint. The final death is usually quiet, lacking the drama of the original death or the brief excitement of resurrection. Star formation rates simply decline as the last gas gets consumed, dropping from a few solar masses per year to less than 1, then to less than 0.1. Eventually, star formation stops entirely when the final molecular clouds collapse or get disrupted. The galaxy's blue regions fade as the short-lived massive stars die without replacement, and the red color reasserts itself across the entire system. Within a few 100 million years, all trace of the resurrection disappears. the galaxy looks exactly like it did before the revival, a smooth red elliptical filled with ancient stars. Only detailed spectral analysis can detect the brief episode of star formation that occurred, visible as a slight chemical enrichment and a small population of stars slightly younger than the bulk. The galaxy will remain in this state essentially forever, its stellar population aging slowly over trillions of years, gradually fading as stars exhaust their fuel and die. There will be no further resurrections, no more brief returns to life, just the long, slow fade into darkness. Zombie galaxies teach us that galaxies are surprisingly resilient, capable of briefly recovering from death when circumstances allow, but ultimately doomed once trapped in hostile environments. The resilience shows up in how eagerly dead galaxies seize opportunities for resurrection. Even a small amount of fresh gas, just a few 100 million solar masses from a minor merger, is enough to trigger intense star formation that can temporarily rejuvenate the system. This suggests that dead galaxies retain the structural capacity for star formation even after billions of years of dormancy. Their disks, though lacking gas, preserve the gravitational potential wells needed for gas clouds to collapse. Their spiral structures, though faded, leave imprints in the dark matter and stellar distributions that can channel gas toward the center. The galaxy isn't fundamentally broken by death, just starved of fuel. Give it fuel and it roars back to life, at least briefly. However, the temporary nature of resurrection reveals the ultimate futility of fighting hostile environments. No matter how vigorously a zombie galaxy restarts star formation, no matter how many solar masses per year it converts into stars, the hostile cluster environment eventually wins. The galaxy can experience resurrection after resurrection, but each revival is shorter and weaker than the last until finally no resurrection is possible, and death becomes permanent. This pattern appears throughout the universe in various contexts. Zombie galaxies in the densest cluster cores barely resurrect at all. Their revival attempts strangled almost immediately by extreme ram pressure and thermal heating. Zombies in moderate density environments experience longer resurrections, but still ultimately fail. Only zombie galaxies that somehow escape cluster environments entirely, perhaps flung out through gravitational interactions, stand any chance of permanent revival and return to healthy star formation. Those cases are extremely rare, representing far less than 1% of all dead galaxies. For the vast majority, resurrection is merely a brief intermission in the inevitable march toward permanent death. We are living in a golden age that we didn't even realize was special until recently. Right now, at this precise moment in cosmic history, 13.8 billion years after the Big Bang, the universe is alive with star formation. Galaxies across the cosmos are actively converting gas into new generations of stars, creating the brilliant light shows we observe when we point our telescopes at distant spirals and starbursts. This epoch of vigorous star formation has been ongoing for roughly 10 billion years, beginning a few billion years after the Big Bang, when the first substantial galaxies assembled, and continuing through to the present day. But this golden age is temporary, a brief chapter in a much longer cosmic story. We exist during what future cosmologists, if any exist, will look back on as the stelliferous era, the age of stars, a period that represents perhaps 2 to 3% of the universe's total potential lifetime. Before this era, the universe was too young and too hot for stars to form. After this era, which will end in approximately 100 trillion years, the universe will have exhausted its fuel, and no new stars will ever ignite. We are privileged observers, witnessing cosmic phenomena that will eventually become impossible to see, living during the narrow window when galaxies are alive and the universe is bright. Future observers, if they emerge billions of years from now in the corpses of dead galaxies, will inherit a radically different cosmos, one so dark and empty that they might never discover the truth about their origins or the history of the universe they inhabit. Imagine you are an astronomer living 10 trillion years from now, a time frame so distant that it dwarfs the current age of the universe by a factor of 700. You live on a planet orbiting a red dwarf star, one of the last stellar remnants still burning hydrogen after nearly all other stars have died. Your planet is located in what was once a massive spiral galaxy, though you have no way of knowing that because all evidence of galactic structure disappeared billions of years ago. When you look up at the night sky, you see nothing. No stars, no galaxies, no nebulae or star clusters. Just perfect blackness in every direction, except for your own dim sun. Your telescopes, far more advanced than anything we possess today, can detect nothing beyond your local solar system. The cosmic microwave background radiation, that faint afterglow of the Big Bang that current astronomers use to study the universe's origins, has been redshifted into undetectable radio wavelengths by trillions of years of cosmic expansion. The distant galaxies that we observe today have accelerated away beyond the cosmic horizon, their light redshifted to infinity, effectively removed from the observable universe. You have no evidence that anything exists beyond your solar system, no proof that the universe had a beginning, no indication that stars and galaxies once filled space in vast numbers. You might develop theories about physics and mathematics, but you could never discover cosmology because all the evidence has been erased by time and cosmic expansion. This is the fate awaiting future civilizations that emerge too late. They will be born into a dark universe stripped of the clues needed to understand cosmic history, prisoners of an observation window that has permanently closed. The observation window, that period during which the universe provides evidence about its own origins and evolution, is finite and closing. Right now, we can observe the cosmic microwave background radiation, measuring its temperature fluctuations and using that data to constrain models of the early universe. We can observe distant galaxies at various stages of evolution, watching how star formation rates have changed over cosmic history. We can measure the expansion rate of the universe and detect the acceleration caused by dark energy. We can observe the large-scale structure of the cosmic web and use it to test theories about dark matter and structure formation. All of this is possible because we live during the observation window when these phenomena remain visible. But cosmic expansion is closing this window progressively. In approximately 150 billion years, most galaxies beyond our local group will have been carried away by expansion beyond the cosmic horizon. The light from these galaxies will be redshifted to such extreme wavelengths that no telescope, regardless of its design, could detect them. The cosmic microwave background will have cooled to less than 1/1000th of a degree above absolute zero, and been stretched to wavelengths longer than the size of the observable universe, making it effectively undetectable. The evidence for the Big Bang will have vanished. Future astronomers looking at the sky will see only the handful of galaxies in their local supercluster, all of which will have merged into a single giant elliptical galaxy by that point. They will observe a static universe containing one galaxy surrounded by emptiness. They might conclude, reasonably but incorrectly, that this galaxy is the entire universe, that nothing exists beyond it, that the cosmos has always existed in this state and will continue forever unchanged. They will be unable to discover the truth because the universe will have hidden its history behind an impenetrable barrier of expansion and time. The universe functions as a vast ecosystem where galaxies are born from primordial gas clouds, live by forming stars for billions of years, and die when their fuel supplies run out or environmental conditions turn hostile. This galactic ecology follows patterns eerily similar to biological ecosystems on Earth. Just as forests contain trees of different ages, some young and growing, others mature and stable, still others old and dying. The universe contains galaxies at all stages of evolution. Just as predators hunt prey and organisms compete for resources, galaxies merge and cannibalize each other, competing for limited gas supplies in crowded environments. Just as organisms are born, reproduce, and die, galaxies form through gravitational collapse, spawn new generations of stars, and ultimately fade into darkness. We happen to witness the living phase of this ecosystem, the period when birth rates still exceed death rates, when new galaxies are still forming from primordial gas, and existing galaxies continue vigorous star formation. But this balance is shifting. The universal death rate is accelerating while birth rates decline. Fewer new galaxies form now than formed in the early universe, because most gas has already been incorporated into existing structures or heated to temperatures too high for collapse. Meanwhile, more galaxies are dying as they fall into hostile cluster environments or exhaust their fuel supplies. The ecosystem is aging, moving inexorably toward a state where death dominates completely and new birth becomes impossible. In the far future, the galactic ecosystem will resemble an old-growth forest, where all the young trees have died, leaving only ancient giants slowly decaying with no seedlings to replace them. Eventually, even those ancient giants will fall, leaving a barren landscape devoid of life. The inevitability of galactic death extends even beyond the hostile cluster environments we have been discussing. Even galaxies that avoid clusters, that orbit in splendid isolation in the voids between large-scale structures, will eventually die due to cosmic expansion driven by dark energy. Dark energy, the mysterious force causing the universe's expansion to accelerate, is slowly but inexorably spreading galaxies farther apart. As the distance between galaxies increases, the cosmic filaments that connect them, those streams of gas and dark matter that allow material to flow between structures, get stretched and thinned. Eventually, these filaments break entirely, severing connections between galaxies. An isolated galaxy surrounded by ever-expanding empty space loses access to external gas supplies just as completely as a cluster galaxy loses access through strangulation. The mechanism differs, but the outcome is the same. The galaxy must live on its internal gas reserves alone, with no possibility of replenishment. For a while, this is sustainable. A galaxy like the Milky Way contains enough gas to sustain star formation for perhaps another 5 to 8 billion years at current rates. But eventually, the gas runs out. Star formation ceases. The galaxy turns red and dies. Unlike cluster galaxies, which might experience zombie resurrections from minor mergers, isolated galaxies in an accelerating universe have no such possibility. Cosmic expansion ensures that no other galaxies will ever come close enough to merge. no gas-rich dwarfs will wander into range. The galaxy dies permanently in isolation with no chance of revival. Dark energy guarantees that this fate awaits every galaxy in the universe eventually, regardless of environment. The timeline varies. Isolated galaxies might survive 1 trillion years while cluster galaxies die in 1 billion years, but the endpoint is identical. Cosmic acceleration is slowly killing the universe by strangling future galaxy formation and starving existing galaxies of the fuel they need to survive. The acceleration, discovered in 1998 through observations of distant supernovae, means that the expansion rate of the universe is increasing over time. Space is stretching faster now than it was 1 billion years ago, and it will stretch faster still 1 billion years from now. This accelerating expansion has profound consequences for galaxy evolution. First, it prevents new galaxies from forming in the present epoch. Galaxy formation requires gas to collapse under gravity, but accelerating expansion works against gravity, making it progressively harder for material to collapse into bound structures. Any gas clouds that have not yet formed into galaxies probably never will, because acceleration will spread them too thin for gravitational collapse to occur. Second, acceleration separates existing galaxies at an increasing rate, breaking apart structures and isolating systems from each other. Galaxy groups and clusters that are gravitationally bound can resist expansion, but anything not already bound will be carried apart. The cosmic web is slowly dissolving as filaments stretch beyond their breaking point. Third, acceleration drives away the gas reservoirs that galaxies need for long-term survival. The diffuse intergalactic medium, that vast reservoir of gas between galaxies, gets spread thinner and thinner by expansion until its density drops below the level where galaxies can accrete it. Galaxies become islands in an expanding ocean, cut off from external supplies and forced to live on internal reserves. The acceleration rate is actually increasing as dark energy becomes the dominant component of the universe's energy budget. Matter and radiation dilute as the universe expands, their density decreasing over time. But dark energy maintains constant density, meaning its relative importance increases as other components fade. Eventually, dark energy will dominate so completely that it tears apart not just galaxy clusters but individual galaxies, solar systems, even atoms themselves in a catastrophic end scenario called the Big Rip. Even if we avoid that extreme fate, acceleration ensures a slow death for the universe, a gradual slide into cold, dark isolation where no new structures can form and existing structures slowly fade. The Milky Way, our home galaxy, is a temporary oasis in this dying universe. For now, we orbit in a relatively safe location, far from the deadly cluster cores where RAM pressure stripping murders galaxies by the hundreds. Our local group remains gravitationally bound despite cosmic acceleration, meaning we will not be torn apart by dark energy in the foreseeable future. The Milky Way contains enough gas to continue forming stars for billions of years, and when we eventually merge with Andromeda, the collision will trigger a final burst of intense star formation that could last for 1 billion years. Our descendants, if humanity survives that long, will witness one of the most spectacular events in galactic evolution, the death throes of 2 giant spirals merging into a massive elliptical. But even this temporary reprieve must end. After the Milky Way-Andromeda merger consumes all available gas and creates the elliptical galaxy Milkomeda, star formation will cease. Perhaps 5 to 7 billion years from now, our home galaxy will join the graveyard. It will turn red as the last massive stars die. Its spiral structure will dissolve into a smooth, elliptical profile. No new stars will form. No new planetary systems will coalesce. No new opportunities for life will emerge. Milkomeda will drift through an increasingly empty cosmos as cosmic acceleration carries other galaxy groups away beyond the horizon. Eventually, in the far future, Milkomeda might be the only galaxy remaining in the observable universe from the perspective of any observers within it. They will live in a dead galaxy floating in empty space, unaware that their home was once part of a thriving cosmic ecosystem filled with trillions of galaxies. The Milky Way is our temporary oasis, a place where conditions support life for a cosmically brief window. We should appreciate this privilege while we have it. The implications for the search for life and intelligent civilizations throughout the universe are profound and somewhat disturbing. If star formation has a finite window, and if life requires stars and planets to emerge, then life itself has a limited time period during which it can arise. We are living during that window now, but the window is closing. In the future, as more galaxies die and star formation rates decline throughout the universe, fewer planets will form. Fewer opportunities for life will emerge. Eventually, star formation will cease entirely, and at that point, no new life can arise anywhere in the universe. Any life that exists at that point will be the descendants of organisms that emerged during the Stelliferous Era, our current golden age. This creates a cosmic urgency for life to emerge now, during the present epoch, because future epochs will not support the origin of life. Consider the timeline. Star formation will continue at gradually declining rates for perhaps another 100 trillion years, as the longest-lived stars, the red dwarfs, consume their fuel. After that point, no new stars will form anywhere. The last stars will die approximately 10 trillion years later, plunging the universe into permanent darkness. Any life that has not emerged by then will never emerge. Any civilizations that have not developed by then will never develop. The universe has a finite window for the origin of life, and that window is perhaps 100 trillion years long. This sounds enormous compared to human timescales, but it is vanishingly brief compared to the potentially infinite future stretching ahead. If the universe exists forever, as current cosmology suggests it might, then the era of life represents an infinitesimally small fraction of cosmic history, less than 1/1,000,000,000 of 1% of the total timeline. We exist during that brief spark of activity before eternal darkness falls. Intelligent life faces an even narrower window. While simple life might persist for trillions of years, eking out existence around dying red dwarf stars, complex multicellular life requires more energy and more stable environments. Intelligent civilizations capable of astronomy and cosmology require stable planetary systems around long-lived stars in galaxies where conditions support technological development. These requirements constrain intelligent life to an even briefer window, probably no more than a few 100 billion years. After that point, most galaxies will be dead. Most stars will have exhausted their fuel, and the resources needed to support technological civilizations will become too scarce. There is a cosmic deadline approaching, not for humanity specifically, but for the potential emergence of intelligence anywhere in the universe. Any species that develops intelligence after that deadline passes will find itself in a dead universe, unable to observe the evidence needed to understand cosmic history, trapped in darkness without the resources to expand or explore. This creates a perspective of cosmic urgency. Intelligence must emerge now, during this narrow window, or it will never emerge at all. We do not know if we are early or late in this window. Perhaps intelligent life is common throughout the present universe, with millions or billions of civilizations existing simultaneously across countless galaxies. Or perhaps we are rare, one of the first or possibly the only intelligence to emerge during this window. Either way, the window itself is temporary and closing. Every year that passes is a year closer to the end of the era when intelligence is possible. Every galaxy that dies reduces the number of potential homes where future civilizations might arise. We are living during the universe's brief flash of consciousness, the narrow epoch when matter organizes itself sufficiently to contemplate its own existence. The galactic graveyards we observe throughout the universe are previews of the ultimate fate awaiting all cosmic structures, including our own galaxy and everything we have ever known. When we observe dead galaxies in the Coma Cluster, or measure the declining star formation rates in distant galaxies, or study the zombie galaxies briefly resurrecting before dying again, we are watching the universe practice for its ultimate end. The mechanisms that kill galaxies in clusters today will eventually kill all galaxies everywhere, as cosmic acceleration spreads them apart and severs their connections to external gas supplies. The transformation from blue spiral to red elliptical that we document in cluster environments will eventually occur in every galaxy throughout the cosmos. The galactic graveyards are not isolated phenomena affecting only unlucky systems that fall into hostile environments. They are universal previews of what awaits every galaxy. The Milky Way will become a graveyard galaxy. Andromeda will join the graveyard after our merger. Every spiral, every elliptical, every dwarf galaxy will eventually exhaust its fuel and die. The universe is filling with corpses, and eventually only corpses will remain. This is not a pleasant realization, but it is an unavoidable conclusion from our observations and our understanding of cosmic evolution. The universe is not eternal and unchanging as ancient philosophers believed. It is not cycling endlessly between expansion and contraction as some 20th century cosmologists hoped. It is expanding, accelerating, dying. The galactic graveyards are our future. They show us where we are headed as a civilization, as a planet, as a galaxy. Everything we have built, everything we are, everything we might become exists during a brief intermission in the universe's march toward darkness. This perspective should fill us with both humility and purpose. Humility because we recognize our cosmic insignificance, the temporary nature of our existence in a dying universe. Purpose because we realize the precious rarity of our situation, alive and conscious during the narrow window when the universe permits such things. We are witnesses to the universe's golden age, observers privileged to see galaxies alive and forming stars, able to study the cosmic microwave background and measure the expansion rate and understand where we came from. Future civilizations, if any exist, will not have these privileges. They will inherit a dark universe stripped of evidence, unable to discover the truth we have been fortunate enough to glimpse. We live in the age of light, brief and brilliant, surrounded by gathering darkness that will eventually consume everything. The galactic graveyards remind us of this truth every time we observe them, showing us the inevitable fate that awaits all structure, all complexity, all life in the universe.